Hello, everyone. This is Billy Younger, and I'm here for Physics Solutions. And I'm going to work a typical statics problem or a common statics problem that you'll find in an algebra-based or a calculus-based physics course. Statics is the same thing as applying Newton's second law, but it's a special case where Newton's second law has the acceleration equal to 0. That means the object could be moving in a constant velocity. Remember, velocity has a magnitude in direction, and a constant velocity means it can't change direction or speed, or how fast it's going. But it can also have a zero velocity that stays zero. That's acceptable as well. So that's what a statics problem is. And the typical one is regarding trying to use a tree to pull a car out of a mud bog or something. So let me start by sharing my screen so that you can see the problem we're solving. So here I go, share screen. I've typed it up and hopefully made it large enough for you to be able to read it on whatever screen you're reading. It says some physics students are trying to get a car stuck out of the mud. They estimate the force they will need to get it out is about 20,000 newtons. And I just told everybody to assume set 5 sig figs there. Again, I don't care too much in my classes about sig figs, but some instructors do. So I try to at least point out where the sig figs are going wrong. In order for the way that I use sig figs, in order for this to have 5 sig figs, I would have had to put a dot right after that 0 as a decimal. So I would have to have a decimal on the end, and then that would be 5 sig figs. Often your books will treat that as 5 sig figs without the little decimal, and that's fine too. But I'm just going to assume that one has 5 sig figs. So some physics students are trying to get a car stuck out of the mud, and they estimate the force they will need to get it out is about 20,000 newtons. They use a heavy strap and attach one end of the front to the front of the car and the other to a large sturdy tree and proceed to push on the strap horizontally at its middle as shown. So I'm splitting the difference between that strap dead center so that both the angles will be symmetric, and that makes it a little easier. If the angle when they apply the force is 3 degrees, how large must the force be? So that's the first part of the problem. A is how large must F be to get a tension in that rope equal to 20,000 newtons. Part B is once that force is applied, they realize the strap stretched way more than expected and the angle is now 9 degrees. So what's the actual pulling force on the car at that time? So that's the big question. You can see this is supposed to be a car, obviously not a very good drawing of a car, not a very good drawing of a tree, more like a gumball. But the more important thing is you get what we're trying to draw here. So the way I'm going to attack this is I'm going to make a free body diagram for this point on the rope right here where the F is touching. Okay. I have to do it that way because that's the only place where F and the tensions are actually being applied. So notice I have a tension pulling up into the left from the car, and I have the same tension pulling up into the right, pulling towards the tree, and then I have the force F pointing down, and that's what I'm wanting to know. So we've got all our figures, 3 degrees, 20 newtons, and then later it turns to 9 degrees. So let me stop share and let's solve the problem. So the first thing I'm going to do is draw a free body diagram, and then I'm going to use my Newton's laws of motion, F equals ma, basically, technically for each of the dimensions. But in this case, if we're calling horizontal the direction between the center of the car and the center of the tree, if we're calling that the x direction, then the x equation is not going to matter. It's really all that matters will be the y equation. So let's get cracking. I'm going to turn on my document cam. So what we have here is a coordinate axis that we always want to draw when we're doing our free body diagram, so we can agree what's positive and what's negative. That's going to be my positive x-axis. That's going to be my positive y-axis, and the origin I'm going to put a little dot, and that's going to represent that little piece of rope I told you about. So with that little piece of rope, I can now apply the forces that are acting on it. For one, I have a force acting in the negative direction, that is F, and that's the force that I want to know. It's already along a coordinate axis, so I'm going to go ahead and draw it a specific color. Specifically, since this is a negative direction, I'm going to call it red, like a stoplight. And F is the question mark. Then I have a force that's not aligned along the axis, so I'm going to draw that black, and it looks like this. Now that's the tension in the rope, and of course that angle right here was 3.00 degrees. but that means that angle is also 3.00 degrees because they're what we call alternate interior angles. This is like a railroad track. That's the other railroad track. And if they're parallel, like railroad track should be, and you lay a piece of 2x4 across it, the angle interior to the railroad tracks, but on opposite sides of the 2x4 will always be equal. So that's the rule from geometry that we're using. And then we'll have a similar one on this side. It's also at 3 degrees. 3.00 degrees. I'm sorry about how small I'm writing that, but you got the figures from the original problem, so it should be fine. Let me do this. Okay, so neither of those are actually acting along the coordinate axis, but when I break them down into components, they have to be. That's the whole purpose of coordinate axes. So I've got a green means go, red means stop. So that's a positive coordinate, and I'll call that positive t. Notice this is 3 degrees as well. So that's the sign. So t sine 3.00 degrees. Positive is that component. Again, on this side, I have a t as well, and those two are identical. We often sort of wave our hands on why they're identical, but the main thing is here that by symmetry, they have to be identical. So basically, I'm applying a force this way. That has to be held up by a tree, but that also has to be held up by a car. Hence, the pull should be about the same. Now, over here, I also have a positive y component, which I'm going to represent with the green again. And that one is also positive t sine 3 degrees. Okay. But I also have a positive x component for this one over here. And that's positive t cosine 15, or excuse me, 15, where did that come from? Positive cosine 3 degrees. This one, on the other hand, is a negative x component. So I'll draw it like this. And this is just negative t cosine 3.00 degrees. Again, that's 3.00. So you can see right here, this is another way it's telling us, obviously, that the t's must be equal, because all the forces acting on this spot of the rope, and the spot of the rope, once it reaches that 3 degrees, essentially is in equilibrium, so it can't be moving. Because of that, the only way this could be true is if this t and this t were identical, because those two have to add up to give you 0, and they both are multiplied by cosine. So yeah, this is part of the proof that, in fact, the t's are equal. So now that we have that, I can see that this x one's not very useful. All I really need to consider then is the summation of forces in the y direction. And that is the summation of the forces in the y direction equals mass times acceleration in the y direction. Now, what we're using really is Newton's second law of motion, which says the total force, the sum of all the forces acting on a particular object, is equal to the object's mass times the object's acceleration. And notice they're vectors. And since mass is a scalar, and it can't be negative, m times a has to be parallel to what's on the other side. So once you add up all the forces, you get a net force. That net force has to be parallel to the acceleration. In our case, though, we're actually considering statics, which is this point of mass on the rope is not it's not moving with any speed at all, much less changing speed. In fact, the acceleration is 0. But remember, statics applies not only to things sitting perfectly still, but to things moving at constant velocity. In this case, it's just sitting still, though. So that's our summation of forces in the y direction equals mass and acceleration in the y direction. It just tells us that the summation of forces has to be 0. The forces that we see are t times the sine of 3.00 degrees. That's positive, plus t times the sine of 3.00 degrees minus f, and that's all equal to 0. So from that, you can see that f is going to have to be, and this is part A, just to remind you, f is going to have to be 2 times t times the sine of 3.00 degrees, which I can now plug that in. That's going to be 2 times 20,000 newtons. That just allows me to write it again because I got 5 sig figs times the sine of 3.00 degrees. Making sure your calculator is actually in degrees as opposed to radians. You can compute this, and I'm going to do it now. I've done it once already. I just want to make sure I didn't make a mistake. So this is my third run. 2 times 20,000 times the sine of 3 degrees, and I get 2093.4 newtons. Now, this had 5 sig figs. That only had 3. And the way we generally treat a trig function or a logarithm or something like that is if you put in 3 sig figs, you get out 3 sig figs. So really, these last 2 digits are not really significant. So I should call this 2.09 times 10 to the third if I was sticking with trig significant digit rules. So with that, basically we apply 2090 Newton force, and we should get 20,000 newtons as the tension in the string, and that's going to be in the strap, that is, and that's going to be the force that's pulling the actual car. Now in part B, they say, when we actually applied that force at 2093.4 newtons, we ended up causing the band to stretch, the strap to stretch more than expected. And in fact, we ended up getting 9 degrees. So we might as well draw another free body diagram just to make sense of it. But now we've got a tension. Obviously, I really blew that degree out of proportion. That's, almost 40 degrees or almost 45 degrees. But we also have another one that's supposed to be about the same. So remember, these drawings aren't perfect, but I think you get what I mean. So anyways, that's the tension, and that's the tension. But now the rope is making a 9-degree angle with the horizon, which means it's 9 degree with this one too. But we still have the force F being in the negative Y direction. And F has a magnitude of 2093.4 with underlines there, just to remind you, we only have 3 sig figs. I'm also going to put that this is the Y-axis and this is the X-axis, and I'll just do that with red pen. I can see that this component, of course, is negative. So this will be negative T cosine 9.00 degrees. And then all the others are actually going to be positive. So this will be positive T cosine 9.00 degrees. This one will be positive T sine 9.00 degrees. And this one will be positive T sine 9.00 degrees. So again, we're going to take the summation of forces in the Y direction because that's the only one that matters. In fact, the X direction just confirms to us that the tension is equal on both sides. So I'll say the summation of the forces in the Y direction is equal to mass times acceleration in the Y direction. But again, this is a statics problem, so the acceleration is 0. Ultimately, I get 2T sine 9.00 degrees minus 2093.4 newtons is equal to 0. So I can see that T is going to have to be, when I pull this to the other side, it'll become positive 2000. In other words, when I add 2093.4 to the other side, it's going to cancel out on this side, and the other side is just going to become 2093.4. And then all I have to do is divide by 2 in the sine of 9 degrees. So I get 2093.4 newtons over 2 times the sine of 9.00 degrees. And this will be what the tension actually turns out to be. So when I do that, I believe I get 6,691.1, but I want to double check. So 2093.4 divided by, when you do a division like this, you want to make sure you use parentheses, because your calculator, otherwise, if you don't use parentheses, will be doing 2093.4 divided by 2, and then it'll multiply that by the sign of 9. So always make sure you are careful with things in the denominator by using parentheses. So with my calculator, I put 2093. I'm going to say 2 times. Now do my trig function. And that's going to be sine of 9.00 degrees. And that gives me 6,691 91 newtons. And that's still 1 sig fig more than we're supposed to have. So I should probably really call this 6.69 times 10 to the 3 newtons. So we got considerably less in reality than the 20,000 newtons we wanted, just because the strap stretch. We would hope, obviously, that the physics students overestimated the force required and that this was actually sufficient. If not, they just have to push with a larger force. So that's it. I hope that makes sense to how to solve that physics problem. Remember, you just got to consider the equilibrium of something to do a statics problem. In this case, it happened to be something fairly insignificant, specifically the spot on the middle of the road. So I hope that helps. Have a good day.